Autonomous performance in dynamic adversarial environments is a major challenge, and while over 14,000 teams worldwide compete annually using teleoperated robots, we created an autonomous robotic system for this year's Vectorbox competition, Pushback, to beat a human driver one-on-one. Pushback is a back-and-forth race to score your blocks and goals while your opponent tries to do the same. The robot can intake blocks from the field and store them in its hopper and outtake them at each of the 3 goal heights. Our primary computer is an NVIDIA Jetson AGX Orin, which commands the robot's operation. We have 4 global shutter cameras mounted to the corners of the robot that are synchronized and processed by a secondary Jetson Nano. These images are sent over Ethernet to the primary Jetson. For localization, 2 stick ladders are mounted to the back of the robot along with an IMU. The primary Jetson communicates with the VEX brain over an RS-485 connection via a custom PCB to command motor powers and receive encoder readings.
Our software stack is built around ROS2. We use the Navigation 2 framework with AIMScale for localization of the LiDARs, IMU, and odometry, MPPI for path planning, and a system of behavior trees to implement robot actions through a central action server. We also use ROS2 control using an omni-wheel drive controller to control the robot base, velocity commands for the intake motors, and a custom hardware interface to communicate with the VEX brain. We developed the whole software stack first in simulation, using Gazebo with a URDF model of a robot to be able to test with. We implemented facilities to play the full game in simulation, including scoring and intake, as well as a simplified simulated opponent for a robot to play against.
The vision model localized objects on the field given 4 onboard cameras. The images are first processed by a shared ResNet with 13 million parameters, then a transformer along with positional embeddings encoded as sine and cosines, then individual heads that predict box dimensions, x, y, z, and class. We use greedy cost matching with distance threshold for evaluation. The model does well at detecting closer objects, and we achieve sub 2 cm medium precision for localization. Misdetection include occlusion or out-of-view objects. However, this issue can be mitigated by aggregating temporal information using Bayesian updates.
Here's an overhead video of the field along with a view of the 4 cameras mounted on the robot.
The strategy module is in charge of creating the strategy for the robot to do at a single step. The input is the current field state and the output is the action state. The training pipeline follows an asynchronous rollout generation and training. Training is done with PPO and general advantage estimation function. The evaluation uses true skill as a metric, and as you can see in 26,000 typesets, the model was able to converge to around 160 of true skill.
This is the strategy model simulating a game with 2 robots.